In this presentation, I will be introducing the work for our paper, IDE Augmented with Human Learning Inspired Natural Language Programming, which proposes the HiSyn extension, a natural language programming tool integrated with the Visual Studio Code IDE. So before getting into the details of the tool itself, first I want to cover some background and motivation behind natural language programming. Then we'll discuss HiSyn, the Human Learning Inspired Synthesizer, which is the framework that underlies our natural language programming tool. And then lastly, we'll discuss this tool's integration with the Visual Studio Code IDE and give a quick demo of the main functionalities of this extension and the typical use cases for it. So firstly, what is natural language programming? Well, simply put, natural language programming is the process of using a code synthesizer in order to automatically generate output code or programs from some natural language input query. For example, here is a use case for the air travel information language, which is an SQL-like language used for querying air traffic control information. And here we see an English sentence translated into a query for this domain. As one can imagine, there are numerous use cases for natural language programming, pretty much all of which rely on some general user who is either A, completely unfamiliar with programming in general, or B, is a programmer who just is unfamiliar with the language required for the task at hand. In both cases, instead of expecting the user to go through the arduous process of learning the language and directly writing the program for the task, instead a natural language programming tool can be used to translate a natural language description of what the user intends to accomplish into the working program that accomplishes the task. As mentioned, this can be used by both general users who don't know programming and programmers alike, but for our particular tool, the target audience is specifically programmers and programmers who are working with domains that feature very large and complex API sets. Some examples of these types of domains include the AST matcher domain for the parsing the AST in the LLVM project, as well as the TensorFlow library used for machine learning in Python. Both of these domains feature hundreds of APIs, and most of which are extremely complex with numerous parameters and are just in general very difficult to use. Typically, in order for a programmer to write some working code in these domains, it requires constantly checking the documentation, and instead of going through this process, instead a natural language programming tool can be used to quickly generate the working output code expressions from just a natural language description of what they intend to accomplish. Because of these use cases, especially among programmers, these types of natural language programming tools have seen a large spike in popularity and interest in the past several years. But despite this popularity, they have been found to be extremely difficult to develop. Most of the current solutions all feature a data-driven approach, which relies on machine learning models such as RNN and GNN models that are trained on hundreds of thousands and millions of labeled training examples. This approach has shown some success. For example, the GitHub Copilot tool. However, there are some weaknesses to this approach, primarily the reliance on these large numbers of training examples. These training examples can be extremely costly to collect and in some cases are just not feasible or available for certain domains. For example, domains that just aren't very popular or used in kind of niche fields, or domains which just don't have widely available examples online. So to address these issues, we propose HiSyn, the Human Learning Inspired Synthesizer, which, as opposed to the data-driven approaches, features a natural language understanding-driven approach, which is intended to mimic the same thought processes that a programmer goes through when developing a program. So the way this works is that we first start with an understanding of the API documentation and grammar for a domain, and we combine this with an understanding of the intent behind a user's query in order to generate the final output code expressions. The advantage of this approach is that it requires absolutely no training data, and because of this, it is much more extensible to new domains. Okay, so now let's try and get a better understanding of how this HiSyn tool works. So shown here is an overview of the framework for HiSyn. This framework features a modular design, which is comprised of three main components. The first of which is the domain knowledge constructor, which processes the API documentation and grammar used during code synthesis for each domain. Next, there's the front end, which uses natural language processing to translate each natural language query into a dependency graph, uses the intermediate representation during code synthesis. And then lastly, there's the back end, which uses a novel grammar graph-based translation algorithm to generate the final output code expressions from this intermediate representation and domain knowledge. Okay, so next let's kind of look at how each of these components work at a lower level by using a running example from the ATIS domain described earlier. Specifically, we're going to be using the following English language query. I would like to find the cheapest flight from Baltimore to Atlanta. Okay, so for this domain, the first thing we'll look at is the domain knowledge constructor, which, as mentioned earlier, is responsible for processing the grammar and API documentation for the ATIS domain. So first, for the grammar, we will transform this into the shown grammar graph, which is used as the search space when generating the output code expressions. Additionally, the API documentation is parsed in order to grab the name, description, inputs, outputs, etc. for each API in the domain. This will primarily be used in the backend when semantically mapping between the input query and the possible candidate APIs in the output code expression. Next, we'll look at the front end. So as mentioned, the front end is responsible for translating the input query shown above into a dependency graph used during code synthesis. So to accomplish this, we use a number of natural language processing techniques, primarily light regularization, part of speech tagging, lemmatization, named entity recognition, and dependency parsing in order to translate the sentence into the dependency graph shown below, which is also pruned to remove unnecessary function terms before being passed to the backend. So in the backend, we go through the arduous process of translating the dependency graph shown for our query into a final output code expression. The first thing we do in order to accomplish this is semantically map each token at each node in the dependency graph into a list of candidate APIs. So that is potential APIs that could represent each of the nodes in our dependency graph. And specifically, this will be used because in the final output code expressions, we will select exactly one of these candidate APIs for each node. So next, we look at all the possible combinations of this dependency graph by selecting a candidate API at each node and translate this into a final output code expression using reversed all paths search algorithm. So the way this works is we start with a transform dependency graph like the one shown, which has a particular candidate API at each node. And for each edge in this dependency graph, we search our grammar graph from our domain knowledge constructor for a subgraph that connects the APIs at each end of each edge. For each of these, we could end up with multiple paths, but the one that is chosen is the one that has the minimum number of APIs. The idea behind this being that this is the path that will reduce redundancy. So using the shown dependency graph on the left, we end up with the following 5 paths, one for each of the edges shown on the right. And with these paths for each edge, next we combine them into a final graph by attaching the child path to the end of the parent path. And in some cases, there will be overlap in the siblings, in which case we simply merge these overlapping prefixes when necessary, as shown in the example here. And the result of this is the graph shown on the left, which is translated directly into the final output code shown on the right. Okay, so now that we understand at a high level how HiSyn works to translate our input queries into output code expressions, let's see how well it works on the general domain. So in our case, we evaluated HiSyn on 3 different domains. First, the text editing domain, which is used for text editing in Office Suite applications. Next, the mentioned ATIS domain, used for querying air traffic control information. And lastly, the mentioned AST matcher domain for parsing the AST in the LLVM project. So when evaluating on these 3 different domains, we find that HiSyn has an overall accuracy of at least 80% on all 3 domains. That is, the code expressions generated by HiSyn are exactly the same as the ground truth code expressions in at least 80% of the test cases. For the first 2 domains, this is on par with the leading data-driven approaches for these domains. And for the AST matcher domain, this is significantly better than the leading rule-driven based approach. So the conclusion being that HiSyn is comparable in accuracy to the current leading approaches, and in some cases significantly better when the domains feature a much more rich API set. And the advantage of this is that HiSyn requires absolutely no training examples whatsoever. Okay, so now that we know HiSyn works and how it works, let's see how to actually use it. So as mentioned, the intended audience for HiSyn is programmers. And with that in mind, we have decided to integrate the tool with the Visual Studio Code IDE, which is one of the most popular IDEs currently on the market used by programmers. The main features of this tool are first and foremost the ability to leverage the natural language programming made available through HiSyn, as well as some additional domain support for the domains currently supported by HiSyn. For example, there are code snippets for typical use cases in these domains, as well as additional commands for the AST matcher domain for building tools in the LLVM and Clang project. So next, we're going to show a quick demo of this Visual Studio Code extension in use using 2 example use cases. First, we will be creating a Clang tool for the AST matcher domain, and then we will actually be extending HiSyn itself to a brand new domain, specifically the regex domain for the Python language, and using it on a very simple program. After installation, the HiSyn extension can be accessed within VS Code by selecting its icon in the left side panel. This will open up the extension's main interface, where various commands can be run using the icon buttons, and information can be viewed in its tree-like structure. In this example, we're going to be using the AST matcher domain to build a Clang tool for the LLVM compiler, a typical use case for this domain. To do so, we're going to be leveraging both the natural language programming features available through HiSyn, as well as additional domain-specific tools available in the extension. To get us started, we're going to use the Clang tool template code snippet in order to build the basis of our program. This can be inserted by either clicking on the snippet in the extension interface or typing its name directly into the code editor. So this template builds a tool which simply matches all for loops in a given source file. We're going to make this a little bit more complicated by matching specifically for loops where a single variable is initialized with the integer value 0. To do this, we're going to use HiSyn's natural language programming feature by clicking on the play button in the extension interface or searching for the run HiSyn command in VS Code's command palette. This will open up a series of input boxes where we first select our domain, and then we submit our natural language English query. In this case, I'm describing the code I want by saying find all for statements whose initialization portion declares a single variable which is initialized to the integer 0. Then I submit it to HiSyn, where the resulting code can be directly inserted into our program. Then I can save it, and then click on the file to directly build this tool into my local LLVM project. First, I give it a name. Here, calling it my Clang tool. And once it's successfully compiled, we can actually use this tool to run it against some source files. In this case, I'm going to run it against a file that has 3 loops in it, but only one of which it should match, which contains a single variable initialized to the value 0. We can run it by selecting the file and selecting the Run Clang Tool command available through the extension. Then we simply pick our new tool, and the output will be displayed in a new command terminal. And here we see that the correct for loop was indeed matched. By default, the HiSyn extension runs using a HiSyn engine located on a remote web server. Currently, this HiSyn engine only supports the AST matcher, flight, and text editing domains. However, the extension can also be configured to run using a local HiSyn installation, which may feature different domains. To use a local HiSyn installation, we can select the status icon shown below to switch to local mode, and then configure the extension by submitting the path to our local installation in the settings. After doing so, we should be able to view and add new domains to our local installation. In this example, we're going to be adding the regex domain for the Python language. To do this, we simply need to submit the API documentation and the grammar documentation for this domain. This can be done in the extension interface by clicking on the Add Domain icon. This will open up a series of input boxes where we first submit the name of our new domain, followed by the grammar and API documentation. Then it will automatically be built into our local HiSyn installation and be available for natural language programming. To demonstrate this, we'll do a simple text editing example. So we will hit the play button to run our natural language programming, select our new domain, and in this case, my text editing example, I'm going to be replacing all white space with new line characters in the text Sally sells seashells by the seashore, but only for the first 3 lines. So we can submit this to HiSyn and then automatically insert the generated code into our Python file. And now we can run this in a new terminal to make sure it works. And here we see that it successfully edited our text.